The next slide is 23 years of energy demand by region, with the years redundantly coded in color and position. Just imagine that there's a line graph at the top of each, and it'll be simpler and easier. So on the left we have North America, then Latin America, Europe, former Soviet Union, Middle East, Africa, and Asia. See the enormous rate of growth of energy use in Asia. The unit here, millions of tons of oil equivalent, is a unit equal to 0.04 exajoule, and at the foot of the slide I give you some other units. A barrel of oil equivalent is 6 gigajoules. A million barrels per day is 2.24 exajoules per year. But that's how the energy field is. It's very confusing. Next slide is the projection of growing world energy demand by sector. And here you see 1971, 2002, 2030. The sectors being transport in dark green, power in yellow, orange is industry, and other sectors, residential, are light green. And the global primary energy sources in the past 35 years, oil at the top, coal, gas, hydro, and nuclear, about equal. 5% of the world's energy source. I told you 17% of the world's electrical power, but only about a third of the energy used by the world goes into electrical power. And here's a pale version of the spaghetti chart for the world of primary energy sources on the left and end-use categories on the right, in units of millions of barrels of oil per day equivalent. The world uses 186 million barrels of oil per day. The U.S. uses 21 actual million barrels of oil per day. In the next slide we meet BAU, which means business as usual. The composition of the primary sources is shown in the stacked graph as the bar graphs on the left, and the annual growth rate on the right, greatest for other renewables, which have been growing at 6.5% per year, but they are a tiny element, tiny fraction of the total, although growing very rapidly. They are the red at the top. Biomass and waste is the next, and so on, down through coal at the bottom. The oil supply and cost curve, to which I will return, shows a major part of the world energy problem. Here we have the economic price in U.S. 2004 dollars, not much different from 2008 dollars, plotted versus available oil in billions of barrels. This is a supply curve for oil and the amount of cumulative supply needed by 2030, and its uncertainty are shown in the World Energy Outlook required cumulative total to 2030. So we're down here, and by 2030 we will have used that much oil. It could have been satisfied by the already produced oil and the OPEC and Middle Eastern oil, as shown here. Note that all that oil is at a cost less than $20 a barrel. And even the...
Could you explain this table a bit more?
Yeah.
I fail to understand.
So over here, available oil in billions of barrels on the right, 1,000 billion barrels has already been produced. If we produced all of the oil from OPEC in the ground there in the reserve, that'll be another 1,000 billion barrels. Other conventional oil, North Sea and elsewhere, higher cost, $25 a barrel per production. So this is the equivalent, the economic price, 2004 US dollars. Costs about $25 a barrel to produce the oil. Of course, the producer will sell it for as much as they can get for it. I will discuss this further. Then we see deep water oil, up to $35 a barrel, no matter how deep it is. Arctic oil, not so deep typically. Some of it is deep, but with the further problem of the ice cover. The enhanced oil recovery here in the purple, in which one pumps down CO2 or does other things to increase the recovery of existing oil fields. Heavy oil or bitumen or tar sands, and then oil shales, that is rock-containing oil, that costs a lot more to produce. If one produces heavy oil, and which requires a lot of energy to produce, then and disposes of the extra CO2, it increases the price to something like $70 per barrel. So this is the supply curve, how much it costs to produce oil up to 5,000 barrels cumulative. I will talk about this more. Yet the world is paying a global price exceeding $120 a barrel at present, with talk of $200 a barrel or more in the future. Here I show how difficult it is to replace gasoline or diesel fuel for road transport. Here is gasoline with its energy density in megajoules per gram, gigajoules per kilogram, about 0.03, compared with batteries, way down here on the chart, or chemical hydrides or liquid hydrogen. And the Department of Energy hopes to do better with the storage of hydrogen as an energy carrier. Another criterion is volumetric energy density, megajoules per liter, and gasoline or diesel fuel excels there as well. It is a wonderful material for bringing energy to a mobile, to a vehicle. The batteries don't put carbon dioxide into the atmosphere from the vehicle, although they may very well do so in the manufacture of electrical energy to charge the battery. Here I show how relatively simple it is to provide liquid fuels, in principle, for transport from any of the primary energy sources on the left. Natural gas to liquids via syngas, this synthesis gas, equal parts of carbon monoxide and hydrogen that were produced for many years and sold as town gas as a means for powering furnaces and industry. Biomass can be made into syngas, as can the extra heavy oil, and that can be converted to hydrogen as an energy carrier, methanol, or even to normal liquids, naphtha, gasoline, diesel fuel, and so on. But it costs money. Germany did this during the Second World War. South Africa produces much of its fuel from coal in this process, a coal to liquid process, putting all of the carbon dioxide into the atmosphere. Note that if one makes vehicular fuel from biomass, there is no net carbon dioxide put into the atmosphere because the carbon was withdrawn from the atmosphere in the previous growing season. There's not a lot of biomass available in the United States. For instance, here's the annual U.S. carbon used in the form of gasoline, diesel fuel, and then coal, natural gas. And here, that used as paper, corn, wheat, and so on, is only about 15% of the carbon in transportation fuels. But we could, in principle, grow more biomass. The conversion of corn to ethanol is a very bad idea, and people who voted for it ought to suffer electorally because the rest of the country and the world are suffering. The International Monetary Fund estimates that 70% of the growth in corn prices over the last 2 years is due to the corn to ethanol industry, and 40% of the growth in soybean prices.